Welcome everyone, Brian here. So today we're going to talk about the first big idea, which is going to cover the simpler concepts of chemistry. We're going to be focusing on Coulombs Law and then different questions you're going to be seeing that will show up in the AP Chemistry exam. Remember, this is not intended to teach you every single little thing about chemistry, but more so specific practice for the AP Chemistry exam, especially because it's arriving so soon. Your exam is the 9th, I believe. That being said, let's get started. So the first thing that we're going to talk about is a carbon atom. You know, in the periodic table, you'll have letter C right here. You're going to have a number up here and then another number down here. This number corresponds to the number of protons. And then this number corresponds to the average atomic mass. And that will be the main focus right now. How exactly does this get calculated? We should know that there are two variations to every atom. First, you can change atoms by messing around with the number of neutrons, and that will create an isotope. Then you can mess around with an atom by changing the number of electrons, and that creates an ion. So let's work with isotopes for a second. This is going to come up from a specific graph known as mass spectrometry. Sorry if I butchered that. So your graphs will look as follows, and I guarantee you'll see at least one of these show up somewhere on the AP exam. You are going to have on the x-axis the mass number, and on the y-axis a percent abundance. This is supposed to represent every naturally occurring isotope of that specific atom. So let's talk about atom X, for instance. So some atom that we're creating. You might see a 0.5 up here or a 50 on the y-axis, so 50%, a 0.3, and a 0.2. Then on y, we'll assign random values. Let's call this one 74. Here we're going to do 76, and here 77. So how would you calculate the average atomic mass of this given atom X? So atom X's mass, the average atomic mass, which is a weighted average of every different version that occurs, is going to be exactly that, a weighted average of these values. So we start with the one that occurs 20% of the time. His mass is 74 times 0.2 plus 76 times 0.3 plus 77 times 0.5. Whatever this comes out to be will give you that average weight, that weighted average value. As far as the mass number itself is concerned, that will be the mass number is always number of protons plus the number of neutrons. So the only thing we're bearing here is the number of neutrons, right? Because they are all isotopes. Awesome. Moving on. Let's define the mole. So many of you should be familiar, we definitely have to be familiar with the idea of a mole right now, but we're going to make sure that we're all on the same page. The mole represents a number. That number is going to be 6.02 times 10 to the 23rd. This number itself is known as Avogadro's number. The idea of a mole is that you have this number of things. These things, quote unquote, specifically correspond to ideas in chemistry. So we can use formula units, we can use electrons, we can use protons, we can use ions, atoms, molecules, and the list goes on and on. All these different ideas that we're going to be working with in chemistry. A mole works in the very same way that if we say the word dozen, immediately you think of donuts and 12. The word dozen isn't necessarily reserved for donuts, but most of the time it just so happens to be that way. When we talk about dozens, we're typically talking about donuts. Same exact thing with moles in chemistry. Now, moving on, let's talk about Coulombs Law. And this is the more important section of this whole video. Coulomb's law is given by the following. F equals K Q1 Q2 over R squared. You will never be asked to use this equation and actually plug in values. Instead, what you're going to be doing is looking at it more from a qualitative perspective. So we can set this as a proportion where we remove K. K is a dielectric constant, so it is a constant value, and it's really of not too much concern for us. Instead, we're going to be working with Q1, Q2, and R squared. Imagine you had an electron right here, and then there's a proton right here. This distance between the two would correspond to your R value. The charge of this electron would be Q1, and the charge of this proton would be Q2. We would call this a -1 charge for our purposes, and here a +1 charge. You don't actually need the Coulombic charge of the proton and the electron, just this will be fine. And then R is whatever it ends up being. Now, on a separate case, imagine we have an electron right here, and then a proton all the way over here. Charges remain the same, right? -1 and +1, but what has happened to R? R has increased. So we would say the Coulombic attractions about this electron and proton pair is going to be smaller than that of this electron pair. Why? Because it's further away, and we know that force is going to have an inverse relationship with the radius. Awesome. Moving on, let's give a bit more of a specific example with relation to chemistry. Let's try to compare the lattice energy between sodium chloride and magnesium chloride. So they're going to be very similar in size. You should have a general idea of the trends right now, the three main trends, which we're going to discuss a bit more in a second. But right now, sodium is number 11. It is in the third row. Magnesium is 12, and chlorine is 17. They're all in the same row. The size between the sodium and chlorine, magnesium and chlorine are going to be a decent bit different, but from sodium to magnesium, relatively the same. So their internuclear radius, the difference between the center of each of these nuclei, should be relatively similar. But here, Mg has a charge of +2. Cl has a charge of -1. In order to balance out, you have to have MgCl2. If you look at the actual attraction, so the amount of energy required to break this, it's all going to depend on the force. The one that has a stronger Coulombic forces is going to have a higher lattice energy. So let's do the Coulombic forces, F equals, and again, we're going to go ahead and use a proportion because we know that that K value is going to be the same on both of them. Q1, Q2 over R squared, and then this side for magnesium chloride, Q1, Q2 over R squared. The ion version of sodium has a +1 charge, and then the ion version for chlorine has a -1 charge. And the bottom we'll leave it as R squared. So we know they're going to be relatively similar. Over here, the ion version for chlorine is again -1, but the ion version for magnesium, that's +2, with relatively similar R values. So which one would you expect to experience greater attractions? It obviously have to be this value over here. We get -2 over R squared, where here you get -1 over R squared. So magnesium chloride, which is on this side, has to experience greater Coulombic attractions, so his lattice energy would be greater. Now, there is something we need to talk about in reference to these values. Sometimes, if we're talking about ions in this case, we can use the +1 charge and -1 charge. But what if we're not talking about ions? What if we're talking about something like ionization energies for a single atom? You know that ionization energy is the amount of energy it takes to remove that last electron. Again, we'll go into this a bit more depth first in a second. I just want to talk about finding effective nuclear charges right now in Coulombs law. So again, we'll remove K because for the most part it doesn't really interest us. We have Q1 over Q1 times Q2 over R squared. In the case of an atom, let's do lithium. So I have 3 protons in here. I'm going to have 2 electrons in the first energy level. And I'm going to have 1 electron in the third energy level. So how do we use this whole idea of an effective nuclear charge? Effective nuclear charge and shielding are concepts that are very similar. Effective nuclear charge tells you what positive force this electron is going to feel as a result of the interactions with the electrons and the protons inside of that. So this electron will only feel the effects of these guys. If there were anything along the outside, so say we had another electron out here, it would not affect your effective nuclear charge. We have 3 protons, and effective nuclear charge is always calculated as follows. 3 protons, so a positive 3 value, minus 2 for the 2 electrons that are along the inside. And this gives you a plus 1. My effective nuclear charge is plus 1. Shielding refers to this effect of these electrons canceling out that positive 3 charge. So, if we wanted to use our proportion here, Q1 would be positive 1, in this case the actual effective nuclear charge, and then Q2 would just be 1 electron, so negative 1 squared. Now, how does effective nuclear charge change? Let's do a similar example where we have 3 protons, but this time just 2 electrons. Again, same formula. Effective nuclear charge is going to be 3 protons, but how many, so just 3, how many electrons on the inside of this electron? That's in the first energy level, so there can't be any electrons. 3 minus 0, so effective nuclear charge is positive 3. In that case, if you used Coulombs law, you would get a positive 3 for effective nuclear charge, negative 1 for the electrons, and then R being whatever it is, which we're going to talk about more in just a second when we cover trends. Before we get to that, let's talk about Hund's law, Pauli exclusion principle, and the Aufbau principle. You do not have to have these memorized specifically. What you have to know is how to create any given electron configuration graph. And this is the graphs with the up arrows and down arrows, not the ones that actually give the electron configuration, like 1s2, 2s2, 2p6, all that kind of stuff. Let's work with boron here, carbon, nitrogen, oxygen, fluorine, and neon. We know all these guys are going to be in 1s, 2s, and 2p. Purposely pick these for a reason. When you're filling this out, you always fill out the lowest energy level first. And we'll write off to the side how many electrons are available in each. Boron has 5 electrons, 6, 7, 8, 9, and 10. So I have 2 electrons here. The next 2 electrons go in the next area of slightly higher energy. There. And then so forth. I can only put 1 electron, so I put 1 arrow. Notice there's always going to be 2 arrows in every single little section. S holds 1 box, P holds 3 boxes, D holds 5 boxes, and so forth. So exactly the same as the normal electron configuration rules. And these 2 arrows have to face opposite directions. They're supposed to signify spin of the electrons. You really don't need to know anything about that aside from these arrows have to face opposite directions. So when we go on to the next one, same exact thing, but now we have an issue. Remember, there are 3 separate boxes right here. Whereas in these 2, there are only 1. Would we fill out this pair, or do we go on to the next box? The answer is you always go on to the next box. You want to make sure that you fill out 1 electron in every box before you start dealing with pairs in any given box. And let's fill these all out really quick just so we have them. Obviously they're all going to have this section filled. Now here, I would have one up arrow, one up arrow, one up arrow, and then you start to include down arrows. And the last one has up arrows and down arrows everywhere. This would be a case where the octet is fulfilled, right? You have 8 electrons in the last energy level. Awesome, so let's talk about the trends now. We have 3 main trends in the periodic table. They are, first, your atomic radius, second, your electronegativities, and then third, ionization energy, which is synonymous with binding energy. You can use the terms interchangeably. Sometimes I'll use one or the other, just depending on what's being talked about. They're not exactly the same, but as far as this class goes, yeah, they are exactly synonymous. So, atomic radius. Well, first, your trends are going to follow a certain structure. Atomic radius will increase in this direction. So AR increases. Then ionization energies and electronegativities will increase in this direction. That's the general trend. There are several breaks in this trend. The majority of these breaks are caused mostly because of atomic radius. If we understand why that happens with atomic radius and where the big jumps happen, you'll be able to deduce these breaks on your own. So we're going to talk about atomic radius first. Atomic radius increases as you go down and as you go towards the left. But every time you go down, there is a jump in energy level, right? So every time there's a jump in energy level, R is going to increase greatly. Going back to Coulombs Law, we know that the dependency was Q1, Q2 over R squared. With a big increase in R will come a big drop in F. That will affect both your electronegativities and ionization energies. So let's think about ionization energy for a second, which we briefly talked about. If you had the case where the next electron that we're removing drops in energy level, so its radius gets a lot smaller in this case, what would you expect to happen to the force? It would get much bigger. It would take a whole lot more energy in order to remove that electron from wherever it is. Let's talk about why the trend is the way that it is now. In comparing sodium with magnesium, or do a little bit simpler, let's do lithium with beryllium. Lithium has 3 protons, beryllium has 4 protons. I'm going to put 2 electrons here for each. And then lithium is going to have 1 electron on the outside, whereas beryllium will have 2 electrons on the outside. Cool. What's the effective nuclear charge about this electron? If you were to calculate that, you would get 3 protons, so just positive 3. You would get, if you were to calculate that, you would get 3 protons, so positive 3 minus 2. This electron and this electron. So we get an effective nuclear charge of positive 1. But then, what of this case? If we're talking about this electron, your effective nuclear charge is positive 4, because I have 4 protons, minus 2. Shielding says that we're only worried about the electrons on the inside. This extra electron that got added isn't going to change anything. So we have an effective nuclear charge of positive 2. This electron is going to experience a greater attraction towards the center of the nucleus. So, what does that mean in terms of your atomic radius? We know that the trend says that the lithium atom should be bigger than beryllium atom. Even though we added an extra electron, and it seems as if because electrons repel each other, the whole thing would have to expand a bit. That's not the case. These two electrons are far apart enough from each other that what really determines it is the pull you get from the effective nuclear charge. Each of these electrons feels a stronger pull towards the center than in this case. So by adding that electron, even though there is a small amount of repulsion, imagine if we added an electron without increasing the number of protons, then it would definitely be bigger. But in this case, that's just not true because the effective nuclear charge is increased. That electron will feel a stronger attraction towards the center. Now let's talk about ions briefly for a second. Same case, 3 protons. If I had 3 electrons on the outside, it would take whatever size it does. I add an extra electron. Now these guys all repel each other just a little bit more. So my R would have increased. Versus the case where I have 3 and just 2 electrons, your R would decrease. So when you have ions, adding electrons is going to increase the atomic radius versus taking away electrons always decreases it. But when do those big jumps happen? The first big jump, in this case for lithium, would be removing that electron because now we're in the first energy level. For beryllium, it would involve removing 2 electrons. Then you're going to get smaller jumps every time you fill a subshell. Those aren't as significant. You might see a bigger jump than just between any normal 2 electrons that don't feature this, but there are slightly bigger jumps in between subshells, and then the biggest one is always in between energy levels. Moving on, let's talk a bit more about electronegativities. Electronegativity is how strongly any given atom will pull on electrons in a bond. Imagine a carbon-carbon atom. They're the same element, so they have to have the same electronegativity. They're going to pull each other with the same amount of force, so these electrons are going to occupy roughly the same region of space. We're going to get more into bonds later when we talk about IMFs, but the main thing is that these electrons are going to be shared roughly between the two. Now, imagine in the case of sodium and fluorine. Fluorine has a very high electronegativity, highest in the periodic table actually, and sodium not so much. If you look at the electron configuration, sodium's most common ion is going to be +1 and fluorine's is going to be -1. Sodium desperately wants to lose 1 electron and fluorine desperately wants to gain 1 electron. So in this case, what you're going to have more is a transfer of his electron over to fluorine's. Now, the actual values for electronegativities most of the time are not going to be given to you. Sometimes you may have a question where you're asked to classify them, and then these ranges tend to be a bit arbitrary. So the typical electronegativity values are going to be as follows. There's no noble gases here, by the way. Noble gases don't have any electronegativity values because they don't want to make bonds. Fluorine is 4. Chlorine would be 3.5. Oxygen is 3. Sulfur is somewhere along the lines of like 3.2, and then it changes. It varies depending on what source you're looking at. Electronegativities are used to determine bonds. So, according to some sources, a covalent bond is that which has a difference in electronegativity of approximately from 0.2 to 0.5. Again, this changes widely who you ask. Some values say like 0 to 0.3. Notice this one doesn't include 0 from 0.2. It doesn't matter. It's just so you guys get a general idea. Then polar covalent is seen as 0.5 to around 1.2. Then ionic is 2 plus. Again, obviously there's holes in the values that I've given you. Like I said before, it doesn't matter. If you're asked to classify one of these, they're explicitly going to give you the ranges that they're working with, and then it just becomes a matter of taking the difference. If we had sodium, sodium might have an electronegativity value of like 0.5 or something. So let's do sodium chloride. That might be 3.5 minus 0.5, and you get 3. For sodium chloride, it would fall under ionic, which makes sense because we know that it's a salt, it's an ionic bond. Awesome. Now, moving on. The last topic of discussion will be ionization energies and binding energies. Again, the terms are synonymous. Ionization, though, typically refers to removing the electron from the valence shell, whereas binding, they tend to talk about incoming kinetic energy. So we'll describe it in a second. But again, the terms are exactly synonymous. If you have a atom, we'll do lithium again. So 2 electrons in the first energy level, 1 electron on the one that's most outside. The energy it takes to grab this electron and remove him from the valence shell is my first ionization energy. For the next guy on the inside, it would be your second ionization energy. For the third one, it would be your third ionization energy, and so forth. Ionization energy increases every time you remove an electron. The first one is going to be the easiest. The second one is going to have more energy. The third one is going to have even more energy, and so forth. But again, there are breaks in this trend. In this case, the breaks tend to follow more of big jumps, not the second ionization energy being greater than the third. That doesn't make any sense. Let's look at the first ionization energy. You can imagine that Coulombs Law is again useful here. This is why it's so important. This is going to show up all over the place from a quantitative perspective. If we're looking at the effective nuclear charge, I'll put a little 1 here to refer to the first electron of this guy. It is going to be positive 3 minus 2, so plus 1. Effective nuclear charge of the second guy, the second electron, is going to be positive 3 minus 0. Why? There's no electrons on the inside of this, like we mentioned before. Here we had 2 electrons on the inside. And then the effective nuclear charge, 2, this is a 3, of the third electron is going to be positive 3 minus 0, so the same thing. So F1, we'll do F2 up here, we'll do F3 out to the side. In F1, Q1 is going to be positive 1, Q2 would be the charge of 1 electron, minus 1, and then R squared. In this case is just the normal radius for that specific atom. If we go into F2, you are going to see that first I have an increase in my effective nuclear charge. So the numerator is going to increase. And what happens to R? R decreases greatly because we went from the second energy level to the third energy level. So let's do 3 arrows here to show that great increase. You can expect a big jump in between the first ionization energy and the second one. Then the third one, in reference to the second one, this stays the same, whereas the bottom is going to decrease slightly. Here I have F1, that'll be my constant value, we'll call it. F2 is much greater than F1, and F3 is going to be a little bit greater than 1. Why? This portion stayed the same, and this portion decreased slightly. Now, where else are you going to see this kind of information? You're going to be given something called a PES graph. PES stands for photoelectron spectra. PES. So what is the photoelectron spectra graph, and what does it look like? Photoelectron spectra looks as follows. You are going to have a graph as such. Here, you're going to have the term binding energy or ionization energy, again the same thing, and here is a relative number of electrons. You'll get something that looks like a little peak here, a break in the graph, a little peak here, bigger peak, little peak, and then maybe that. You could be asked, literally with just this information, nothing else, no labeling, nothing, to find out what atom are we looking at. How do you figure that out? These peaks are always going to look relatively the same, and they always correspond to something. What is that something? Luckily, it's the same thing every time. The first one is going to be the first energy level and the first subshell on that energy level, the only subshell on that energy level, 1s2. The next peak is going to be 2s2. And remember, here on the y, we do have relative number of electrons. It's never going to be labeled. You're not going to have like a number 2 here, a 3, and a 4, or 6. What you're supposed to do is compare within energy levels, how tall is this guy compared to that one. But you don't have to do that all the time. You only have to do that at the very end. Why? If I have electrons here, which would, you can imagine, corresponds to a third energy level. This one is all the second. If I have electrons in the third energy level, that means I already have these guys full. So immediately we know this section is going to be 2p6. What about this one? I have electrons in the p subshell, so s has to be full. 3s2, and they all are relatively at the same height. Then right here, we can say that's a little bit bigger than s, so 3p3 would be a good call as to the relative number of electrons. In that case, we have 2 plus 8, 10 electrons, plus 5, 15 electrons in total. Given that this is a neutral atom, we would be looking at phosphorus. Now, binding energy, you know, increases as you start removing electrons, or ionization energy increases as you start removing electrons. So this x graph, the x-axis is actually inverted. If you have numbers here, say it requires 5 joules per mole, 5 megajoules per mole or something, to remove these guys, then over here might be 10, over here might be 20, a big jump, and 100 here. Obviously this doesn't go at infinity, but the main thing is that 0 is actually somewhere over here, not over here like you're used to. Y-axis is normal, it's not going to be inverted. Cool. And the absolute last topic to talk about today is going to be the incoming radiation energy. So your incoming radiation energy, which I'll denote as Re, is going to be your ionization energy or your binding energy plus kinetic energy. What's kinetic energy? Kinetic energy is going to be given by 1/2 mv squared. We'll talk about that a lot more later when we're discussing gases. Ionization energies and binding energies, everything we just referred to. And radiation energy, or incoming radiation energy, is and can be light. Any radiation that's coming and providing energy for this electron. Let's draw a quick Bohr model here. Say it requires 10 joules of energy to remove this guy. If I provide 5 joules of energy to my system in the form of light, do you expect this to move? No, of course not. But if I were to provide 15 joules of energy, yeah, in that case, this would be able to move, and this electron gets ejected with 5 joules of energy. That's exactly what this represents. Incoming radiation is 15. My ionization energy is just 10, and it's not going to be any greater than that. Once it reaches that value, it caps out, and the rest would go to kinetic energy. If it were 25, this again would be 10, the rest would go to kinetic energy. And this were 5, this is supposed to be 10, and this will be minus 5, which means we never really actually ejected the electron. This can only be a positive value. Does it make sense to have a negative kinetic energy? Kinetic energy is a scalar. So the question then becomes, I can give you, I can supply 20 joules of energy and then 50 joules of energy. Who do you expect to move faster? Well, the one that has 50 joules of energy should move faster, or a constant amount of energy and the first ionization energy and the second ionization energy. In that case, let's say we give 20 joules, first ionization energy, give an arbitrary value, let's call it 10. The rest would go into kinetic energy, and then again, constant energy, 20 joules. The second ionization energy, you know, is always going to be higher than this value. Let's call it 15. That would mean I have 5 left over for kinetic energy. So kinetic energy of my second ionization energy has to be less than the kinetic energy for the first, if it's even removed. If there was a big jump featured, this might not be enough energy to actually remove the electron. And that's what they mean when we're talking about incoming radiation energy. Yeah, you'll never see it in FRQ. It might be a multiple choice here and there, but that's pretty much big idea 1. After this, big idea 1, just so you guys understand, the main thing is Coulombs law. Coulombs law is used, as you see, to dictate a lot of these trends and understand why these things are happening. In big idea 2, we're going to talk about a ton about IMFs. IMFs is the other half of explanations for why these things tend to happen, which we'll cover next time. Thank you.